Hey folks, and welcome to my research pitch for Babel, a project that is exploring security extensions for many core heterogeneous systems. So whenever discussing previous designs that tackle the problem of heterogeneity in operating systems, there are two that I want to draw attention to. The first is the multi-kernel design. In this design, you place a OS kernel on each core, and then you have a user space monitor that handles all of the cross-core communication and any sort of state sharing that you want to do. The observation with this approach being that not every core is going to support running an operating system kernel. So M3 builds on top of this idea by saying, okay, well then let's have one kernel core and let's introduce a common hardware interface in the data transfer unit for allowing each of these heterogeneous components to communicate. The disadvantages with this approach is that each of the heterogeneous devices is still reliant on the OS kernel to set up a communication channel between the cores. And on top of that, because you're introducing a totally new hardware component, you could increase the chip size and thus increase manufacturing cost, which would hurt the uptake of this approach. And lastly, neither of these approaches consider how you would introduce security extensions between each of these components. So what are we proposing? Well, what we're proposing is a mechanism where you have your security extension implemented in software. And by implementing it in software, it allows the security extension to be designed in a way that complements the processor's style of processing. And then you support this software with a set of common hardware primitives that are available on all of the processors in the architecture. So the security extension in software can always assume the availability of these hardware primitives. And because the hardware primitives are smaller and more lightweight, it should make chip manufacturing more affordable and not increase the size of the chip too much. How are we going to do it? Well, given the current state of technology, the general purpose hardware is going to be based on RISC-V when available. And then for accelerators that don't support RISC-V, such as graphical processing units, we're going to have to do some form of emulation. Our current preference is to do a multi-kernel approach where there is a minimally configured Linux kernel that runs the device driver for the accelerator, like the GPU, and then having a Babel wrapper that exports the GPU interfaces to all of the other accelerators in the environment. And in terms of the use cases that we're looking to explore, one is memory tagging extensions and exploring if we can provide cross-device memory protection domains. And the second is trusted execution environments and exploring issues such as can we facilitate communications between different styles of trusted execution environments, for instance, trust zone to SGX, and then also exploring how we can integrate heterogeneous accelerators running their own Ts into the environment. That concludes this research pitch. Thank you so much for your attention, and I'm happy to take any questions.